now that we have defined complex numbers, we of course want to use them and do something interesting with it. And what we need for that is basically functions. So we know a lot of functions in for real numbers, you know, exponential function, logarithm, square root, sine, cosine, and so forth. And in fact, all of those have some analog also for complex functions. And in general, what you basically do is you can always go from a function f of x defined on only real numbers to a function f of z defined for complex numbers, in a sense by replacing x with z. So this is obvious. You can do it like for x squared. You can obviously do that. You can just write z squared. And it will be the same as f of x when z is only a real number. So this is there, it's clear. It's more complicated when you think about sine or cosine, but what you can there always do is you can use the fact that a function f of x also has a series expansion, Taylor series. So for example, if I write f of x as sum over n equals to 0 to infinity of the nth derivative of f at point 0 divided by n faculty times x to the power of n, I can define a corresponding complex function by replacing x with z again. So I can do sum over n equals to 0 to infinity f of n of 0, which is, you know, just the same number as we have for the real part, n faculty times z to the power of n. So in principle, this is very general, but it actually turns out that for practical purposes, for the things that we need mostly, it's actually enough to know one complex function in detail, and that is the complex exponential function. And as you will see, knowing that complex exponential function, you can go quite some distance, and from that one also derive other complex functions. So let's look at this complex exponential function in more detail. So the complex exponential function, e to the power of z, which is e to the power of x plus iy, one can show basically by using the Taylor expansion of the exponential function, you can show that this one is the same as e to the x times cosine of y plus I sine of y. This is the so-called Euler identity. And this Euler identity actually I would say, is the single most important formula for complex numbers that you can imagine. So that one you should definitely remember. Now, as I said, you can either say that, you know, I derived this formula using the Taylor expansion. You could also see it as a definition of the complex exponential function. And in either case, what you can actually show is that all the usual properties of the exponential function still hold. So for example, so the usual relations hold, such as, for example, that if you have e to the power of z1 times e to the power of z2, that this is equals to e to the power of z1 plus z2. And you can easily show that from the Euler identity and making use of sine and cosine multiplication theorems. Now, it can be interesting now to look at particular values of this complex exponential function, especially when the real part is 0, because we know that we see here that the real part, that's just the usual exponential part that we know. But then we also have, you know, for the complex part of z, where we have the sine and cosine. So what we find if you just plug in numbers is that e to the power of I times pi, for example, that equals to -1. Well, that's because for pi, the the sine is equals to 0, whereas the cosine gives us a -1. And for e to the I 2 pi, we actually get the same as for e to 0, namely 1. And if we now go, so now we have pi and 2 pi, if we go to pi half, then we find e to the I pi over 2 equals to I. That's because then the cosine is 0 and the sine is equal to 1. And consequently, if we go to e to the minus I pi over 2, we get to minus I. So these are important numbers, and it's actually useful to remember those, because these are simple results that you can often use to simplify your calculations. So, knowing this equation here, that e to the I pi is the same as e to the I times 0 equals 1, that one actually tells you that if we have, in general, e to the y iy plus I times n times 2 pi, where n is some integer number, then that result is equals to e to the I times y. So basically, the complex exponential, if you have a purely imaginary argument, is a periodic function with a periodicity of 2 pi. What is also useful, well, what we saw up here is that we defined the complex exponential in terms of cosine and sine. You can also use, of course, now this Euler identity to do the opposite, to define cosine and sine in terms of an exponential function. And when we do that, then you find that cosine of x equals to e to the ix plus e to the minus ix divided by 2. And sine of x equals to e to the ix minus e to the minus ix divided by 2i. Now, these can be useful identities, especially when we're thinking about doing integration, because integrating cosine and sine is not so easy, but integrating exponential functions is very simple. So that's a common trick in many cases, is to replace cosine and sine by these identities here, and then solve the integral easier. Now, I told you that this exponential function here, complex exponential function, is the most important function. And the reason why this is that we can actually use it to reformulate other operations on complex numbers. And for that, we want to introduce the polar form, which, well, you should actually find, which comes from the fact that, when we look at, our complex number z in the complex plane, we normally describe it, with x and y. But, we can describe that vector also by the angle phi here and by its length. That also gives us the same vector. And in fact, what we can easily see here is that if we define r equals to the absolute value of z, then we see that x equals r times cosine of phi, and y equals to r times sine of phi. But if we now plug that back into this original equation, we see that we get r times cosine phi plus I times r times sine phi. And then you see that with that, we can write z equals to, so we have here r times cosine phi plus I sine phi. And you see that this was actually just a definition of the complex exponential if you have only an imaginary argument. So this is actually the same as r times e to the I phi. Yeah. So yeah, just to remind you, basically now, when we have some number z, then basically what we have is r equals to x squared plus y squared. So this is easy, this is because r equals to the absolute value of z. So given a complex number, you can easily calculate this argument r, the component r. How do you compute phi? Well, for that, you basically need to use trigonometric functions. And in particular, you see that if you divide those two together, then you get a tangent. Now you have to be a bit careful because there's different branches of a tangent. And if you do this whole thing very carefully and write everything out, then you find that a possible solution is phi equals arctangent of y divided by x if x is larger than 0. Pi plus arctangent of y divided by x if x is smaller than 0 and y is larger than 0, and minus pi plus arctangent of y divided by x if x is smaller than 0 and y is smaller than 0. So this is a consistent definition of this angle phi. As I said, it basically comes from the fact that the tangent has several branches, and what we do here with the pi and minus pi is that we choose the right branch. What it actually means, if you think about it, the way that we define the angle phi here was that the angle phi is positive in the upper half plane and it is negative in the lower half plane. So this is the definition that we used here. But it's actually important to be aware that this is not the only possible solution. I can also define phi different because it's, it's an angle. So for example, I could also define it such that, phi is larger than 0 for 3 quadrants, and phi is smaller than 0 only for 1 quadrant. That's also fine. Actually, as I will show you, this definition, it doesn't matter which one you choose. The only important thing is that you have to be consistent, always use the same definition. It does have some influence on what exact values you might get from certain other operations, other functions. But again, this all works out as long as you stick with a particular convention and you don't mix different conventions. And basically, there is an infinite number of possible conventions. And, here I just showed you 2, but, in principle, you can use any other choice too. So in particular, remembering what we had before, that, that this identity here holds, that e to the I plus an integer multiple of 2 pi is actually e to the iy again. We actually see that this angle phi that we have here is anyways only defined up to 2 pi. No? So because we have e to the I phi plus n 2 pi equals e to the I phi, phi is only defined up to multiples of 2 pi. So this is basically what is reflected, that you can have different choices. Now, this polar form is particularly nice because many operations that you can do in complex numbers are actually easier in polar form. For example, I listed a couple of examples here, so let's do those. So one example is, for example, taking z to the power of n. Now let's write z in polar form, namely r times e to the I phi to the power of n. Then, the simple algebraic rules that we know from the real numbers, and as I told you, those basically carry over to the complex numbers too. Well, they just tell us that this is r to the power n times e to the I and phi. Or if I take the nth root of a complex number, again, let's do that in polar form. So I take here the nth root, I get the nth root of r times e to the I phi divided by n. So you see now here in this form, it becomes very simple. You can also do it for logarithm, so the inverse function of the complex exponential. And there we get log of r times e to the I phi. Now we know that the logarithm of a product is the same as the sum of the logarithm of the individual arguments. So we get log of r plus log of e to the I phi. But we know that, logarithm, that's the inverse function to the exponential function. So here we just get the argument of the exponential function, so that this simply becomes I phi. And now here you can actually see that, when you define this logarithm, it actually matters how you define the angle phi. Actually, it also matters in the other cases, also for the square root, for example. And you see that, the numerical value they would get out does depend on what convention you chose. And what this corresponds to is that for these complex functions, you can always choose different branches. Now, for example, for real numbers, you have the same thing for when you have the square root, for example. In the case of a square root, what we want the inverse function to taking something to the power of 2. And, in principle, with the square root, we choose a convention that this is the positive solution to that. But, you could have also have chosen the negative solution. So for the real numbers, you could say the square root has 2 branches. Now, you have the same for the complex numbers, but since we now have a complex plane, you can choose actually, your convention continuously. And this is what you see here, is that you get different branches of these complex functions. Now, in practice, often it really is not so important. As long as you keep the same convention throughout what you're doing, you will be fine. There are some subtle cases, especially when you go to more advanced complex analysis, but this is not what we will cover in this lecture here. Now, let's finally go to multiplication. So when we multiply two numbers, Z1 and Z2, we have R1 e to the I phi 1 times R2 e to the I phi 2. And we see that this just gives R1, R2 times e to the I phi 1 plus phi 2. And there you now see again that if we now go to looking into what the multiplication means when you want to visualize that in the complex plane, then if we have two numbers, say Z1 and a second complex number, say Z2, and for those I have angles here, this is angle phi 2, and here I have angle phi 1. Then we see that multiplying these two numbers together, so Z1 times Z2, well, it basically corresponds to adding the angles together. So the resulting angle that we have now here is phi 1 plus phi 2. So that's something that order. So that's phi 1 plus phi 2. And the length of the vector that we now get, Z1, Z2, the length here is R1 times R2. So you see that also these operations actually can be visualized nicely in the complex plane. The polar form is also very useful if you want to solve certain equations, for example, and I want to show you a very specific example now. So here I say I want to solve this equation here, namely that z to the power of 4 equals to 1. And I want to find all the solutions to that. And in principle, if it's a fourth order equation, there should be 4 solutions. And okay, it's a relatively simple equation, so maybe you see it already. What is obvious, that will be obvious to all of you, is that z equals to plus minus 1 is a solution. But what else do we have? Yeah. And for that, it's again nice to do things systematically. by defining z equals to e to the I phi. Now, I already know that, you know, from this equation that the length of the absolute value of z should be 1. So I already put that in basically here. But with that, you know, I also know that z to the power of 4 equals to e to the I 4 phi equals to 1. And, you know, from what we saw before, you know, if e to the I something equals to 1, it means that the argument must be, the argument here is 4 phi, must be a multiple of 2 pi. And, you know, then I can easily write down the solutions phi, because, you know, for n equals to 0, I get phi equals to 0. For n equals to 1, I get phi equals to pi over 2. For n equals 2, I get phi equals to pi. And for n equals minus 1, I get phi equals to minus pi over 2. And there I see that this gives me z equals to 1. And then if you remember, what we showed just above was that z e to the I pi over 2 is I. Here we have z equals minus 1. And here we have z equals to minus I.